morning, everyone. Today I want to show you how the James Webb Space Telescope is changing the way we see our solar system by tracing the chemistry of small bodies in its outermost regions. It took more than 20 years, nearly $10 billion, and the work of thousands of scientists and engineers across 14 countries to build the largest, most complex, and challenging space telescope ever constructed. This is the James Webb Space Telescope. Equipped with the largest primary mirror ever flown into space, 6.5 meters across, Webb collects more than 6 times as much light as the Hubble Space Telescope, shown here to the right. Webb carries 4 cutting-edge scientific instruments for imaging and spectroscopy. Here you see one example, NIRSPEC. They operate at cryogenic temperatures colder than the surface of Pluto, enabling Webb to detect the faint infrared signatures of distant worlds. Webb is an exploration powerhouse. Scientists are using it to investigate our own origins by studying the remnants left over of the formation of the solar system. To understand what Webb is revealing about small bodies today, we need to go back to the beginning. We start from the protoplanetary disk, the rotating disk of gas and dust surrounding the young sun. This is where the initial chemical inventory of the solar system was set. As the disk cooled, planets formed and molecules froze out at different distances from the sun. Water, carbon monoxide, carbon dioxide, methane, each condensed under different conditions. Planetesimals got imprinted these gradients, and the planetesimals are the building blocks of planets. So while most planetesimals were incorporated into planets, others survived as minor bodies in the outer solar system, preserving early chemical signatures. So objects like comets, Charon, Arrokoth, are survivors of that early population, preserving to different degrees the chemistry they inherited at formation. But inheritance is only half of the story. The image you are looking at shows the solar system after it was reshaped, with small bodies spread across different reservoirs. After the planet formed, the solar system underwent a period of dramatic instability. Planetesimals were scattered outward in what we call the Great Dispersal. Only about 1% survived, becoming today's Kuiper Belt objects, comets, centaurs. So when we are observing these objects today, we are observing the last surviving witnesses of that early instability. Objects that preserved the chemistry they inherited at formation, but also the imprint of billions of years of processing. To understand the origin of our solar system, we must be able to disentangle the chemistry of formation from how the chemistry evolved over time. Why is Webb revolutionizing our understanding of small bodies in the outer solar system? When an object from a distant world enters into Webb, we don't just form an image. We spread the light into its components, like a prism, turning white light into a rainbow. The rainbow is a spectrum and carries diagnostic information. Every molecule absorbs light in its own unique pattern. Those patterns act like fingerprints. So when we observe an object in the infrared, we can understand what it's made of, even from billions of kilometers away. We have used this technique before, but for small bodies in the outer solar system, so small, cold, extremely faint, we could access only a narrow slice of the infrared, enough to see hints, but not the full chemistry. Webb opens a new infrared window where molecular signatures are extremely strong and unambiguous. So Webb is changing our understanding of small bodies, and in particular the chemistry of small bodies in our solar system. Charon is one of the very few small bodies in the outer solar system to have been explored by a spacecraft, alongside the Pluto system and Arrokoth. Therefore, it provides a critical benchmark for what Webb can reveal. In 2015, NASA's New Horizons mission mapped Charon's surface in detail. Bright ejecta blankets revealed the excavation of subsurface material, meaning that when an impact occurs, It punches through the surface and throws deeper material in the surrounding terrains. So those bright regions are windows into Charon's interior. Spectroscopic observations have revealed a surface dominated by water ice, with ammoniated species and organic compounds also present. Yet these observations left us with a fundamental question. Charon formed in the outer region of the protoplanetary disk, where we know carbon dioxide can condense efficiently. We have also clear evidence of excavation, with the fresh material brought to the surface by impacts. So why don't we observe carbon dioxide? Why carbon dioxide seems to be missing from those regions that appear to expose Charon's interior? This question remained open until Webb. Webb provides the wavelength coverage needed to answer this question. We obtained observations of Charon with the James Webb Space Telescope. Webb's extended wavelength coverage provides a far more complete view of Charon's surface chemistry. Observations confirmed previously identified surface compounds, such as water ice, and revealed for the first time a thin veneer of carbon dioxide, possibly excavated from Charon's interior by impacts, including those impacts that formed the bright ejecta blankets we see today. We also observed for the first time hydrogen peroxide, a clear evidence that the water-dominated surface of Charon is being actively modified by energy from galactic cosmic rays and solar wind. These schematics represent what Webb is telling us. Carbon dioxide is inherited. It was incorporated when Charon formed and stored in its interior. Impacts excavate that material and expose it to the surface. They don't form carbon dioxide, they just reveal what was already there. Once exposed, the surface is altered by radiation. Interaction between water ice-dominated compounds and energetic particles from solar wind and galactic cosmic rays leads to the formation of hydrogen peroxide, a secondary product confined to the surface irradiated layer. So Webb enables us to distinguish two processes: inheritance, recorded by carbon dioxide, and surface processing traced by hydrogen peroxide. Thanks to the outstanding work of the SwRI communication and media team, the Webb discovery on Charon reached truly a global audience. The discovery was covered by 800 articles worldwide across science media and major outlets, from space.com to CBS News, with an estimated audience reach of 176 million people. This demonstrates how discoveries enabled by Webb do not only advance science, but resonate far beyond the science community. We now move even farther than Pluto to Makemake, a world orbiting in one of the coldest and most remote regions of the solar system. Makemake is more than 2 billion kilometers farther from the sun than Pluto, and takes roughly 3 centuries to complete a single orbit. The image you are looking at is an artist's rendering. Unlike Pluto, Makemake has never been visited by a spacecraft. Its reddish color is thought to arise from macromolecular organic compounds, produced when methane ice, which blankets the surface much like on Pluto, is altered by sunlight and cosmic radiation. Makemake is among the largest objects in the Kuiper Belt, together with Pluto, Eris, and Haumea. We have seen Pluto up close with the New Horizons mission and discovered a world that was much more complex and dynamic than originally thought. So how about Makemake? While Webb cannot return images of Makemake's surface, it can return something as powerful: information about its composition. Composition is our window into processes we are unaware of. When we look at Makemake with Webb, we see a spectrum extremely rich. We see abundant methane ice, together with other hydrocarbon compounds, products of methane altered by radiation. Ethane, acetylene, and other complex organics are all present, painting the picture of a methane-dominated surface shaped by radiation over billions of years. Yet, when we observe and we zoom into a narrow region of the spectrum, a region we didn't have access before Webb, we see something even more remarkable: the detection of gas above Makemake surface. This discovery makes Makemake only the second Kuiper Belt object after Pluto where the presence of gas has been confirmed. The gas we are talking about is methane. And this discovery makes Makemake even more fascinating because it's no longer an inactive remnant of the outer solar system, but a dynamic world, one where methane ice is still evolving today. The next question is, what is producing this gas? We know that Pluto can sustain an atmosphere in equilibrium with its surface ices. This beautiful image taken by New Horizons shows Pluto's icy atmosphere. The methane gas we detect on Makemake may form the same way. Even weak sunlight can warm surface methane ice just enough to sublimate, forming a thin, possibly transient atmosphere, much more tenuous than on Pluto. But the second possibility is that the gas is released by the subsurface through localized events, similar to the plume activity within Enceladus, Saturn's icy moon. We know from New Horizons that Pluto hosts cryovolcanic features similar to the one shown here to the right. They are inactive, but they are a clear demonstration that interior surface processing can occur even on cold, distant bodies. So at the moment we know from Webb that gas is there. Understanding and discriminating between these mechanisms is the next frontier. So we have seen how Webb is revolutionizing our understanding of these small bodies, specifically with the discoveries of carbon dioxide and hydrogen peroxide on Charon and the detection of gas on Makemake. But also Webb is changing the way we study our solar system. It is challenging laboratory measurements. It is elevating spectral modeling and making more intense the interaction and the synergy with and between spacecraft missions. And in doing so, we are connecting molecules, worlds, and people. Thank you, and I'm happy to take questions.